Hi there, my name is Declan Adams, and this is Lab 1 for Physics 1, which is constant velocity. So to start this experiment, what's the purpose? Mainly, we wanted to focus on comparing the change in position of an observed object traveling at constant velocity to a predicted computational model, and this helped us understand how Newton's laws work in the real world on real objects. And just to clarify, observed means that it's the expo marker, and the predicted is the Glowscript code. So to understand this experiment better, we need to talk about some fundamental physics principles, mainly Newton's first and second law. Newton's first law states that an object in motion will stay in motion at a constant velocity unless acted on by another force. For this lab, we're mainly focused on a constant velocity part of this. Then for Newton's second law, which is basically the momentum principle, which states that momentum is equal to mass times velocity, this relates net interaction between system and surroundings, or the net force, to an observed motion. And net force, seen here, equals the change in momentum over the change of time. Additionally, as two offshoots of Newton's second law, we have the velocity update and position update formula, which will become relevant later in our code. But to summarize quickly, these measure the velocity or position at two different times. And as we can see in the velocity update, if Fnet is truly 0 like we say, then the final velocity should equal the initial velocity. Let's see if that's true later. And so as a brief preview of our results, did the observed position of the expo marker match the predicted position? No. And we'll see why in just a second. So looking at our models, our system was the expo marker that's moving, and our environment was the table, air, gravity, everything else at play. And so continuing our discussion of our system, the forces that we assumed were negligible to see if Fnet was 0 was friction and air resistance. So to set up our experiment, we first recorded the expo marker rolling, like you just saw, at a constant speed in a straight line. Then, using Tracker, we found the marker's position frame by frame to determine the observed position. Then using Glowscript, we created a computational model that predicted what the position should be if there was no forces acting on the marker. Then we created a graph overlaying the change of position over time for both the observed and prediction models. So like I said, here's the observed prediction and tracker. So as you can see, our marker's moving. Ignore the lag because my computer can't handle this very well. But if you see all these little red diamonds, that is the individual frame by frame change in position and thus velocity. So we get a nice position and time table, which is created into a graph. It's almost linear, but not quite linear, and we'll discuss that in a second. And then for some numbers for the tracker analysis, the total time it took for the marker to roll was 2.402 seconds. Our initial position was found to be 0.104 meters, and our initial velocity was found using the change in position, so R1 minus R0, over the change in time, so T1 over T0. And I picked 0.5 because all of the movement before this was relatively negligible and made our velocity really, really small. Now, if we look at the code, we can see that the initial conditions were set up here, with the position being what we found in that table, and the velocity was what I calculated in a couple slides ago, with the change in position over the change in time, helping us determine this number. I chose time to start at 0.5 seconds because that's where the distance becomes a little less negligible without lots and lots of zeros, and that helped my velocity for the calculations. Additionally, delta t was found by taking the 2.408 seconds, which is how long it took for the marker to roll, over the 72 frames. Additionally, this was our final time here if we are assuming that I started at 0. Fnet was 0 because we wanted to see if the final velocity indeed equaled the initial velocity for this predicted model. And like I said before, the velocity update and the position formula come back to play. And looking at our code, very linear, a 3D output. So to discuss this a little bit, we see that our Glowscript data, like I said, was linear, but our tracker data was not linear. So this means that some forces were definitely acting on the tracker data, because if they weren't, it should be linear as well. So maybe some sources of error was that there were, like I just said, surrounding forces. So we now see that friction and air resistance do in fact impact the system. Also, tracker may have had some errors with the center of mass issues or missing frames. And for the video, the marker deviated slightly from a straight line if you were paying attention very closely, so that might have impacted our results. But for some conceptual questions, if positive x and negative x were flipped, the slope would become negative, but the magnitude would stay the same, so not a major difference. And is the net force truly zero? No. Our computational model had a further position than the x1 marker, so there must be outside forces. Thank you.